Hello everyone. So we are going to do the next set of questions from the Jan 2021 organic questions, right? Jan 2021 question paper. So the question is, the pigment responsible for red color in tomato has one functional group. Okay. The correct sentence about the functional group is, see, it very clearly says it has just one functional group. If something is having red color, that means it should have multiple conjugation. Now generally conjugation comes because of double bonds, and probably because at the end they also have some kind of carbonyl group. But it very clearly says it has only one functional group. So if one functional group is there, undoubtedly it has double bond, that too multiple double bonds conjugated, because when it is conjugated you need little energy to excite them, and so little energy comes from your visible range. It does not come from a UV range, and so it absorbs energy from the visible range, and rest it reflects back, and that's why you see the color. And so very clearly double bond is what is responsible. But the thing is, tomato has lycopene and it has a lot of double bonds, so it gets excited, the electron easily get excited from pi to pi star molecular orbital, and because of very high conjugation very little energy is needed, and therefore it appears red. Now if it is double bond, if it is alkene, it should show all the reactions of alkene. First thing is, of course, it will show a reaction of decolorization of bromine water. So you know, when you have alkene, okay, and you add bromine to it, so what is color of bromine? Bromine is brown in color, okay, bromine is brown in color. But once you add it, what happens? Bromine gets added to the double bond. Now since Br2 molecule gets lost, now Br2 is not there, what you are having is bromine gets attached. Now since Br2 gets consumed, the brown color disappears, so decolorizes bromine water. Second is, it gives hydrazone derivative on reaction with 2,4-dinitrophenylhydrazine. This is specific test for carbonyl group. It will be given by both aldehyde and ketone. So you must be knowing this is the aldehyde or So this is the aldehyde or ketone, either of them. If you react with 2,4-dinitrophenylhydrazine, so if NH2 is there, followed by NH, because that's what is hydrogen, NH2, okay, and it says 2,4-dinitrophenylhydrazine, so you are having phenyl group here, and you are having nitro position at 2 and 4. So when you react with this, then H2O is lost and you get hydrazone, so double bond, and it gives, and this is very nice bright yellow color. It gives specific test for your carbonyl group. So that's why they have asked specifically, because you should get doubt about does it have carbonyl or not, but because it very clearly said it has one functional group, so carbonyl group is not there. It's all about alkene. Then it is cleaved with it gets cleaved on reaction with ozone. So we again know, if alkene is there, if you react with ozone, so what happens? First you get ozonoid. If you react with ozone, it forms what is called as ozonoid. So you are having this kind of stuff. Okay, and then when you add water and zinc, this will break up like that and like that. Sorry, it breaks up like this, and you get aldehyde or ketone, depends upon hydrogen is there or not. So it gets cleaved. So of course lycopene also has double bonds, so it will undergo cleavage. It cleaves with ozone. Last is positive silver mirror test. So this positive silver mirror test is test for aldehydes, because in silver mirror test you basically add Ag plus, okay, and Ag plus gets reduced to form Ag. So Ag is silver metal, neutral silver metal, so that is silver color. So you can see on the side of the wall of test tube, you can see very nice silvery silver deposited. So that is what is called a silver mirror test. So once you confirm that it is carbonyl group aldehyde or ketone with this hydrazone reaction, and then you confirm it is aldehyde or ketone by this silver mirror test. So because ketone has R C double bond, I'm so sorry, okay, you are having R C double bond O R prime, okay. So now you cannot cleave the bond between oxygen carbon, sorry, this carbon and this carbon. This is very strong bond. Carbon carbon bond is not easy to break, so this will not undergo oxidation. But if you have aldehyde, then what happens? It is easy to oxidize aldehyde because carbon hydrogen bond is easier to cleave and oxygen gets inserted, and this becomes RCOOH. So in redox reaction, something gets oxidized and something gets reduced. So here the aldehyde gets oxidized to acid, and silver plus gets reduced to silver. So therefore the answer is A and C, right? Whatever said is written here, you can read it. Okay, next question. Hans pyridine synthesis involves several steps. Some of those are, so aldol reaction, Dargens reaction, Mannich reaction and Michael reaction. Now this Hans pyridine synthesis is very important for most of the competitive examination. I have found them many times in GATE, JAM and NET. So please go through it, be very clear about it. It's pretty simple reaction. In this what happens is, you take ethyl acetoacetate, two equivalents, and you react with one equivalent of aldehyde, generally formaldehyde, and then with ammonium acetate. So ammonia is there. So basically what happens, you can see here, this hydrogen, both the hydrogens, they are called as active hydrogen. Okay, why? Because active hydrogen, because you can remove this hydrogen, and therefore because it is acidic to a large extent. If you remove this proton, you get negative charge, and that negative charge is stabilized over this side through ester, and also it is stabilized through this side on the carbonyl group. You get a point? And therefore this is acidic hydrogen. Therefore this is to a certain extent acidic hydrogen. So first step is basically, if you look at very roughly at this reaction, it is something like this. This hydrogen and this hydrogen, they react with oxygen and H2O is lost. This is not the exact mechanism, but something like this. So it is nothing but aldol condensation. Aldol, same thing happens. No, what happens in aldol condensation? You have aldehyde or ketone. You have something like CH3, C double bond O. Imagine if you are having aldehyde here. So C double bond O. Sorry. 1 second. Yeah. So if you have aldehyde or ketone, something like this, then what happens under acidic condition or basic condition? One of the proton is lost. You get CH2 minus. Then this goes and attacks a carbonyl group. I'm not able to write it here. So something like, let me try it like this, okay? So it attacks on the carbonyl group. This becomes CH2. This becomes CH2, and this goes and attacks the carbonyl group, and then H2O is lost. So same thing is happening here. This proton is acidic, and this is lost, which is alpha to the carbonyl group. The proton on the carbon alpha to the carbonyl group is to a certain extent acidic. So this is lost, and this goes and attacks another molecule of aldehyde or ketone, and then oxygen is lost, and that's how it is aldol condensation reaction. So very clearly aldol reaction is one reaction. And then what happens actually is, let me show the mechanism very clearly. So how it happens, first step is this is lost and you're getting this. This is very clear cut aldol reaction. If you have doubt, please Google it, look for the aldol reaction immediately. Okay. Then what happens is, I would have done most of the mechanism. Then what happens, then you react with ammonia. Ammonia forms first enamine kind of stuff. Okay. So you get a double bond here and NH2 here, and then this NH2 goes and attacks here. Now this is important. See, this nitrogen lone pair goes inside and this goes and attacks on the double bond which is formed because of reaction with HCHO. It doesn't attack the carbonyl group, it is attacking the double bond, then this comes here, this comes here. So it is 1,4 addition. Look here, it is 1, 2, 3 and 4. So attack is not at between 1 and 2, not between, actually I should have put here 1, 2, 3 and 4. So attack is not at position 2, attack is not at position 2 here, so that you are not getting 1, 2 addition, but rather attack in position 4, then it comes here. So this is 1,4 addition. 1,4 addition, as you know, it is called as Michael addition. So the reaction happens Michael addition. So the two steps which are involved are Aldol reaction and Michael reaction addition. Okay. So this mechanism is very important. It comes every time. Please look into it. Okay. So let's move ahead to the next one. It says the compounds which gives benzoic acid on oxidation with KMnO4R. So this is very simple. If on benzene ring you have any carbon, okay, on benzene ring if you have any carbon next to it, alpha or the alpha position, and it should have just one hydrogen, okay, and rest can be anything. It can be carbon, it can be just another hydrogen, it can be anything, does not matter, but one CH is needed, and then you oxidize with KMnO4, it immediately gives you benzoic acid. So let us look what are things are there. Now this is the benzene ring. On alpha position, this is the carbon. Carbon valence is 4, so it is having 3 bonds. That means at least one hydrogen is, so at least one hydrogen is here, right? Not at least, there is one hydrogen. So this will get oxidized, will form benzoic acid. This one, this carbon is tertiary carbon. See, it is having 4 bonds. One with this CH3, one with this CH3, and one with this CH3, and one benzene ring. So there is no hydrogen, so this will not get oxidized. What about this? This has CH3 and this has CH3, so it will give you COOH on oxidation, and this also will give you COOH. So as you can see, this is not benzoic acid. Benzoic acid is benzene. On that you are having COOH. Okay. So that is called as benzoic acid. So here such thing does not happen. So C is also not the right answer. A is definitely the right answer, and D also. You see here on this carbon, it has only 2 bonds, so it has 2 hydrogens on it. So this, when you oxidize with KMnO4, it forms benzoic acid, right? So these are the things which I have shown. So this and this is the right choice. Question number 14. The products P and Q formed in the reaction are. So you are having a trans alkene and you are reacting with CFCl carbene. Very important is singlet carbene. So singlet and triplet, let us understand. So these are, imagine if you are having one R group here and one R group here. So this carbon octet is not complete, so it is electrophilic in nature. It accepts electron, okay. And if both electrons are on same carbon, on same orbital, it is called as singlet, and it is less stable than triplet. But imagine if you have one electron in one of the empty orbital, another one on the another, then that is called as triplet. Triplet is little more stable than singlet. So singlet undergoes concerted reaction, immediately it reacts. Triplet need not undergo concerted reaction. It is much stabler, so it can go stepwise reaction. So asking the main product P and Q formed. So one thing is, if anything undergoes concerted reaction to one step, then the stereochemistry or the geometry of the starting material is retained. So let us look here what happens. So these are the choices, and we are not bothered about what is it called as side product, minor product. So basically you see here, this is trans alkene. That means one hydrogen is here, another hydrogen is here. So when it reacts, these both ME cannot be in same plane. So one ME is toward the viewer, another ME is away from the viewer. And then it will give you a pair of enantiomers. Why? Because this is a chiral center. So that's what we have done. Another two chiral centers are there. So this side I have put F behind, now I have put F front. Okay. So you can rotate it and see that they are not superimposable on each other. So P and Q, these are the product. So the answer is option B. So whatever I said is given here. Please go through it. Okay. So the answer is B. Right. Moving on to the next question. The functional groups in the reducing sugar that tests positive with tolerance reagent. So tolerance reagent is same thing. Okay. Silver mirror test. So again, Ag plus gets reduced to Ag and will oxidize something else. So I just now sometime back I told you ketone cannot get oxidized very clearly. Aldehyde gets oxidized. So aldehyde is the right answer. Ketone cannot be the right answer. Hemiacetal. Hemiacetal, I hope you know what is hemiacetal. So hemiacetal is formed like this. You are having some aldehyde, imagine, okay. You are reacting with one equivalent of alcohol. Reacting with one equivalent of alcohol. Once you react one equivalent of alcohol, you get R. This H is already there. H is already there. Then you get one O. I'm sorry. You get one OH here. You get one OH here. And you get here one OR prime. You are getting one OR prime. Okay. So now if it gets oxidized, so you cannot get COH, because even if oxygen comes here, then what happens? You are getting RCOR prime OH, then OH. Such things does not exist, because diol will immediately go back into initial state. So this cannot get oxidized. Acetal means you would have reacted with two equivalents of R prime OH alcohol, and you would have got, instead of one more OH, you would have got one more OR prime. Okay. So this also will not undergo what is called as tolerance reagent test. Silver mirror test will not be given. So only and only aldehyde will go this will undergo this test, and therefore the answer is only option number A. Okay. So whatever said is written here. Please go through it. Now question number 16. Among the following question, the anti-aromatic compound is or RR. Anti-aromatic means it should fulfill all the rules of aromaticity. Only thing is, it should not, instead of having 4n plus 2 conjugated pi electrons, it should have 4n conjugated pi electron. So what are the rules? It should be cyclic. So all of them are cyclic. It should be conjugated. Conjugated means all the orbitals in the system, they should overlap. So you see this pi bond is there. This pi bond is overlapping with this pi bond, but it cannot overlap here because there is no vacant p orbital. There is no p orbital at all. It is sp3 hybridized. So this is not conjugated. You can get out of this immediately. Whereas see here. Here pi bond is there. There is a positive charge. Positive charge means there is a vacant p orbital. This vacant p orbital conjugates with this, which conjugates with this, which conjugates with this, and thus all this p orbital overlap with each other. So the system is conjugated. So still option is there for C. We don't know yet. Now let us look at B. B is also conjugated. Why? Because pi bond in the neighbor of another pi bond, and another pi bond. Similarly, this also all are conjugated. Now what we have to look is, you should have 4n. 4n means n can be 1, 2, 3, 4, anything, and should be multiplied by 4. So if n is equal to 1, so 4n will be equal to 4 into 1 is equal to 4. If n is equal to 2, so 4 into 2 is equal to 8. So this is anyway not conjugate. We'll forget this. Here you see how many electrons are there? 1, 2, 3, 4. 2 pi bonds are there, so 4 electrons. So this is definitely anti-aromatic. Here 1, 2, 3, 4, 5, 6, 7, 8. So B is also definitely anti-aromatic. D is 1, 2, 3, 4. So B, C and D, these three are the right answers. Okay. You can go through it. I will go slowly. You can pause it, read it, and then move ahead. Specifically, I have showed you for option C just to show that how the conjugation happens. So, E positive charge is there, the orbital overlaps, and that's how it happens. This pi bond moves here, you get double bond here, you get positive charge here, and then this moves, you get positive charge here, and then this moves, you get back positive charge here. So, whole system is conjugated. Pi electrons are moving around, rotating around the whole system, and therefore it is conjugated, right? Same way, if I look at this, what happens here? If it is here and here, sorry, so this moves here and this moves here, so this is again conjugated system. This is again conjugated system. Okay, so these are the two conjugated system. Next question. Among the following, the total number of terpenes, terpenoids. Terpenoids is terpenes with OH. So terpenes, you know, is isoprene unit. I have shown you in previous question paper also, if I remember well. So it is having 5-membered ring. Okay, so basically it is something like this and like this. So isoprene unit means 5 carbons are there, 1, 2, 3, 4 and 5. This part is called as head and this part is called as tail. So many of these these isoprene units combine together and give you terpenes. And if anything OH is there or C double bond O is there, then it is called as terpenoid. But important is it will be always polymer of, it will always be polymer of isoprene. Okay, so how many carbons are, if 2 isoprene units are joined together, it is called as monoterpene. If 4 are joined, it is called as diterpene. If 6 is joined, it is called as triterpene. And in between also some things are there. If I remember well, if 3 isoprene units are joined together, 2, if they are joined together, it is called as monoterpene. If 3, it is called sesquiterpene. 4 means diterpene, and 5 something else is there. I am not able to recollect, but something like that is there. Okay. So what you have to see is in this question just count the number of carbons, because in general they will give you all terpene looking system, and count if they are coming as multiple of 5. So let us count how many carbons are there. 2, 3, 4, 5. Then 1, 2, 3, 4 and 5. So you can see here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry. So this is one terpene unit, and this is this is one isoprene unit. This is another isoprene unit. So these are the 2 isoprene units which are joined together, and therefore it is definitely a terpene. It is a monoterpene, cyclic monoterpene. This is one and this is another one. So you can look wherever the isopropyl group is there, triangle part, that is head part. So head and head, something like that is there. So just count the number of carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is also terpene. So here it is 6, then 7, 8, 9, 10, 11. So this is definitely not terpene. Okay. So similarly you can see here 6, 7, 8, 9, 10. This is terpene. 6, 7, 8, 9, 10, 11 and 12. So not terpene. You can see like that I would have done all this job. You can go read slowly. I have explained in great details. Okay. What is meaning of head to head, what is meaning of head to tail, things like that. So total molecules 1, 2, 4, 6, 7, 9 and 10, they all are having multiple of 5. So they are terpenes or terpenoids. So total number is 7. Question number 18. In the following molecule, the total number of possible stereoisomers. Whenever we talk about stereoisomers, always look for chiral center. Chiral center means all 4 substituents are different. So this is the only chiral center. CHOH. So there is a carbon which has hydrogen and OH down, right? And then you have one R group this side, and you are having another R group this side. R prime you can say, not R. If it is R again, then it will have planar symmetry, it will not be chiral. So this is chiral center. So it should have 2 enantiomers, right? So it should, number of stereoisomers should be generally 2. But what happens is, you can see there is alkene. And because of alkene, no E and Z possibility is there. Because of that, number of stereoisomers increase. Only look here, this terminal, no, this both are CS3. So if it is CS3, then There is no question of isomerism. There is no question of E or Z isomerism. But here you look here, one H is, if this H is down and this H is up, then it is Z, sorry, then it is E. And if it was other way, this hydrogen was down, then it would have been Z. So because of this difference, now what happens? Initially two were formed, but each of them is showing star, so you will get 4 stereoisomer. Similarly, come here, you will get E and Z, so total 8 stereoisomers are there. I have written whatever is said, and I have drawn all of them. You can look into it. So ZZ, this is the two possibility. One thing what I have done here is H up, OH down, H up, OH down, H up, OH down. So this is one set of enantiomers, and this is another set of the other enantiomers. Here I have put OH up and H down. And then what I have done is I have drawn all the geometries. So here it was ZZ, here it is EZ, here it is ZE, here it is EE. Here again ZZ, EZ, ZE and EE. Only thing is chirality and the stereochemistry is reversed here. So total number of stereoisomers are 8 in this question. That's it for today. Thank you very much.